Hi everybody, this is Nafish. In today's lecture, we are going to learn how to write down sinusoidal wave in Python, and then we are going to add some noise into it, and then we will convert the signal to frequency domain using the FFT method from Scipy or Scientific Python, and then we are going to remove the noise from the frequency domain signal, and then we are going to convert that signal back to the time domain using the IFFT or inverse Fourier transform from the Scipy module. So the module we are going to use today, let's import those. So import numpy as NP. So for all numerical calculations, we're going to use this, and then we need to have import scipy as SP. So this is the scientific Python package, and where we will have this Fourier transform, inverse of that, and then we need to have some plotting, and for that we need matplotlib dot pyplot as PLT. Okay, so I think we are all set. Let's run this one. Okay, and so let's generate the sinusoidal wave. Okay, so let's say we have a signal S is A times sine, and then 2 times pi times f times t. So moreover, all of us, we are familiar with this equation. We have a is the amplitude and then the sine function, okay, for the sinusoidal wave. So let's define a. A is the amplitude, mostly in terms of voltage. So let's say a is 5 volts, but this is unitless, right? So we'll just not write the unit right here, and then we'll have the frequency. F is, let's say, 20, and then we have the time. So time is the duration of the signal. Okay, so we have to call the npa range. So basically what this is going to do, we is going to create a signal or a time variable from 0 to 1. So the signal is going to start at 0, end at 1, and we need to provide the sampling rate. So let's say delta t, and we haven't defined delta t, so delta t is we have to define here, and for that we need to know how many samples we are going to take to build this signal. So let's say we're going to use 1000 samples. So basically within this time 0 to 1 seconds, we will be using 1000 samples to build the signal. Okay, so delta is the sampling rate is 1 over n, and then we have t here, and then the sinusoidal wave is just going to take this t f pi. So pi is a pi and sine. These functions we need to call the numpy module for that. So np.sine and then np.pi. Okay, so I think we are all set for the very first plot. So let's say plt.plot, and then we have the time t, and we are going to draw the signal S, the sinusoidal wave. Okay, so let's run all of the cells, and okay, so we have gotten our single frequency sinusoidal wave. Okay, so there is only one frequency as we defined, that is 20 hertz. Okay, and as I mentioned, signal is going to start at 0, end at 1. We can use different parameters if we want and different sampling rate. Okay, but for our exercise, we will be using um, couple of other frequencies as well. So basically it's going to be a composite signal. Okay, so rather than having this signal as, let's write it down again, we are going to have couple more frequency components. Okay, so the same signal, but we are going to change the frequency. So this guy and then this guy, and obviously they're going to have different amplitude as well. So let's say the first one is A1, then A2, and then A3, and then the frequency components F1, F2, and F3. Okay, and the time duration is same. Okay, it's a signal of 1 second. So let's define those parameters right here. So A1 is 5, then let's provide A2 and A3. So you can use different numbers here. Let's say A2 is 15, and A3, that is, let's say, 25. Okay, and then we have F1 right here, and let's say F2 and F3. Okay, so F2 is this guy, F3 is this guy. Let's change the frequency. Let's say it's 10, let's say it's 30. So the frequency components are at 10 hertz, 20 hertz, and 30 hertz with different amplitudes. Okay, let's visualize the signal again. So this is the composite signal, and then we are going to plot it, plt.plot, and then we have time t, and then our signal s. Okay, let's run it. We have to run from beginning because this cell we didn't run, so run everything. Okay, and here we go. So this is our composite signal. Okay, so X level is same as the previous one, but you see the amplitude got changed because we have used different amplitude for different sinusoidal wave, and they will add up or subtract depending on the phase. But yeah, this is basically the signal looks like for now. Okay, so this signal S, we are going to add some noise to it, and then we are going to use the FFT to convert it into the frequency domain as mentioned before. Okay, so we have signal here, let's add some noise into it. So S and signal with noise is nothing but we take this signal, and this got like multiple frequency components. Okay, three frequency components. So we have the signal and then np dot some add some random noise. Okay, with zero mean, so the mean is zero and the standard deviation, let's say 0.5. Okay, and let's also give some amplitude into the signal. Let's say the noise amplitude is 10. Okay, I'm just making it up, so let's plot the signal and look, and let's see how it looks like. So plt dot plot and t sn. Okay, this is signal with noise, so let's run it. Okay, we see like there is very little distortion here, it's hardly noticeable. So let's add some more noise into it. Okay, so let's say here it is um let's say 9. Now so the amplitude of the noise is like 20. Okay, then run it. Okay, I think it's not doing anything. Let me see what's going on. np.random.normal. Let's run from the beginning, from the top. Okay, okay, so am I plotting the right one here? We are adding noise. Sn is S, signal S. We have this guy, and then np.random.normal, and this is zero mean. Oh, we have to define the number of samples, which we have not defined. So number of sample is n. Okay, so let's run it. This time this should work. Okay, so this signal is like very much distorted, because we are adding like the noise is multiplied by 20, the amplitude is 20, and then we will have like zero point 0.9 standard deviation, so this is huge. So basically, if you see these two signals, one is without noise and this is with noise, and basically we are going to convert this signal to the Fourier domain, and we will see the peaks or the frequencies we can distinguish from the noise floor. So basically, remember, we had the frequencies right here, 20, 10, and 30. So if we do the FFT, we can show like we have the frequencies, and this can be discernible from the noise floor. Okay, so let's move into the frequency conversion. Let's use the fast Fourier transform. Okay, so the signal we're going to use the FFT on is SN, and so S and then FFT is, we have to call the Scipy library. So SP dot FFT dot FFT. So inside the FFT module, we have the FFT. Okay, and then we are going to take the FFT of this SN signal. Okay, so this is it, and also we have to get the frequency component of that. So fric is sp dot fft dot I think it's fft dot, let's press tab fric, and here we have to input two parameters. One is the number of samples, and one is the delta t. So delta t and number of samples is n. Okay, so let's run it. um, Scipy.fft has no attribute called freak. I think this is something else. I can't remember. Let's have FFT freak, I think. Let's see. Yeah, there you go. Okay, let's run it. Okay. And n should be an integer. Maybe the order I have mistaken here. So first we have to provide the number of samples, n, and then delta t, which is the sampling rate. Okay, let's run it. Hopefully this will go. Okay, so now freak is like the frequency. So here we had the axis in time domain, right? So this function will convert that axis to the frequency domain. Okay, we can in fact see this. Let's run freak, and you see we have all the frequency components. But first, let's plot this signal and see how it looks like. So plt dot plot, and then we have freak, which is the frequency axis, and then this term, this is a complex number. Okay, in fact we can even see it, and that is coming from, if you remember the equation we're having for fast Fourier transform, that is definitely going to give you a complex number. So now let me show you that number first. I think that is also important. So to visualize, you see, most of the numbers, in fact, all the numbers are complex. Okay, so here, what we can do for plotting, we will just take the absolute value. Okay, so absolute value of Sn fric, and then plot it out. Okay, and basically here we see, we have three peaks, one, two, three, and three on the other side of zero. This is because we have, if we do the fast Fourier transform, it's going to get two-sided signal. Okay, one is the negative frequency side, one is the positive frequency side. We are going to trim out the negative frequency components and only just keep the positive frequency components. Okay, so from here, um, what we need to do is like, let's just plot it first. So here freak is, let's take only the positive numbers. Okay, so freak is equals to, I think it's greater than equals to 0. Okay, and same thing with this guy. So freak is greater than equals to 0. Okay, and let's now plot it out. Okay, you see, uh, we have three peaks at 10, 20, and 30, and this is kind of, well above the noise level. You can definitely find out those frequency components. We can, in fact, zoom it out a bit. So let's say axis, and then we have we have to define like how much we want to zoom in. So let's say 0 x-axis for 0 to let's say 100, maybe 50, and then for y-axis we have 0, right? So let's have 1000. Okay, um, 1000 to 12. Okay, this is the one. Okay, let's run it out. Okay, we have to write down plt.axis here. Okay, you can see the frequency components at 10, 20, and 30. You know, you can in fact also automate this one. Like, rather than looking into the plot, you can just do another thing, which is using the function peaks. So let's say we want to know where the peaks are located, right? So peaks is equals to sb dot find peaks. I think it's in numpy, so np dot find, or maybe it's in scipy. Let's see, sb dot find. Oh, I think there is a signal. Okay, signal. There has to be a signal. So signal dot find peaks right there. Okay, and then what we need to define is you know the signal, first of all, which signal we are providing as input. So this is the signal we have right here. Okay, have that one, copy that, and also need to have the threshold. So basically, you know uh, for plotting we used a threshold of 1000. We can use the same here as well, and basically it's going to give you any signal beyond that. So run it and look into the peaks, and you see like we have peaks at 10, 20, 30, and some other frequencies as well. Maybe we can use a threshold that is a little bit higher. So let's say we are going to use 2000. Okay, and now look into the peaks, and you see we got only 10, 20, and 30, and um, this is the amplitude level of those signals. Okay, so now here also you can do a couple of other things, like rather than plotting in this domain, like you can convert this plot into in a logarithmic scale. So 20 times log, I think it's powered, so it's, but we haven't done the PSD or power spectrum density, so it's still in the voltage. So 20 log 10, and then uh, run it, and log 10, that is from the numpy module. So hopefully this will clear out. And we don't see any plot because we have the axis right here that is defined. So let's silent that for a moment. Okay, so this is in dBA scale. Okay, dB. So how much dB down or uh, how much dB up, the signals are from the noise level. Okay, from the noise floor. I can see like it's around 25 dB. So here, uh, you can just change the axis a bit. So from, let's say, you can also normalize this signal if you want. Okay, so from zero, rather than starting from zero, let's start from um, 30, and then let's go up to 80. Okay, oh sorry, for x-axis, from, let's say, from 0 to 80, and here we will go from 40 to, let's say, 100. Okay, so this is in dB scale. Okay, so this is in dB scale how it looks like, and if you normalize this, that will even look better. Okay, so even if so the concept is like, if we do the fast Fourier transform, we can easily find out the peaks which are embedded inside noise. So remember the signal we had. This is the signal. This is kind of very much noisy. We used a standard deviation of 0.9 with amplitude of 20, and if we go into the frequency domain, that inherently got some um, denoising effect. So basically the peaks we had, we can easily discernible. Those are from the noise floor or some other frequency components along the axis. Okay, so we can also eliminate these noisy signals right here, and then convert the signal into the time domain using the IFFT, which I'm going to show right now. So where is the signal? I think it's right here. Okay, so here it is. So we have the frequency, and this is the FFT component, right? So now um, let's copy these things, and so since we're going to use those right here, so this is the frequency component, and this is the frequency axis. I don't think we need this guy right here. So now we have to do some um, filtering, right? So um, SP and then FFT. This is the signal, and basically what we're going to do is we will just use the threshold. Okay, remember we use 1000 right somewhere there. So basically the threshold we're going to use is 1000. We can use 2000 as well. The threshold, right, if you forget, like, just going to show you what threshold I meant, in not in logarithmic scale, just in the normal scale. Okay, so absolute value, and yeah, let's run it out. Just come back to the normal scaling. Okay, so if we use like a threshold of like around 2000, probably we are going to reduce or eliminate all the noises and only keep the frequencies we need. Okay, so um, SP underscore FFT, and here we are just going to let's say filtered, and then we are going to use the where function from numpy. So np dot where. So then we need to provide a condition, and the condition is this guy right here. Whenever this guy is above 1500, take the value from ss fft, and if it is not satisfying the condition, just replace it with 0. Okay, so this is what we're going to use, and then run it. Went through, no issue. And then let's convert it back to use the I50 to convert it back. So SP, then filtered this dot I, this is the variable, so IFFT, and then call this guy and apply I50 on that. So SP dot FFT dot IFFT, and then inside that just use this guy and run it, and let's plot it out. So plt dot plot. So this is now in time domain. So t, and then this filtered version, right? So filtered version. Okay, and write it down. Use absolute of that. Okay. Okay, and now we can see they are kind of very closely on top of each other. We can use 1500 as well, and that will pass some more noise. Let me see. Okay, you can see the blue line that is kind of started passing some noise. You can use 500 as well, and you can see the more noise is also getting into the system. So here it is. So basically this is how we can use a threshold, and the threshold you can use like you can just automate it. Use the peaks function to get the lowest value, and from there you just need to go couple hundred up to the design to find out what value of threshold you're going to use to eliminate the noises, and then use the IFFT. Okay. Hopefully the lesson was useful. Take care.